Okay. Check. Yes. Okay, I will try to. Okay. Sorry.
There is a connection problem. You think
Yes,
there is a
here sometimes the connection just disappears sometimes, Professor.
Okay.
So I would like to read the CV for Professor Chang Won-Yoon here. So he is currently in the Department of Chemical Engineering, Pohang University of Science and Technology. I remember one of the top 5 best university in Korea, and for the KS ranks is above 100, is like a 70, and it is the top university. So luckily I have a Professor Chang Won-yoon in Postech. So he graduated his PhD degree in University of Pennsylvania from 2003 until 2008, and doing the postdoc and also doing as a senior principal research. When I met him, he was in the KIST Center, Hydrogen Fuel Cell, doing hydrogen energy research. So from 2010 to until 2021. So in Pohang, in Postech, he also, other than in Postech, he has a position as a director or research fellow in Research Institute of Industrial Science and Technology on hydrogen and low carbon R&D laboratories. So this is an I mean, when we have a class about hydrogen energy, Korea yang ya sangat baik ya, di mana Profesor Yun ini akan memberikan kuliah berdasarkan ekspertisnya beliau tersebut. Okay, without further ado, Professor Yun, probably you can start your lecture about this hydrogen in the first session of this hydrogen energy lecture from Professor Chang Won-yoon. Yes, the time is yours, Professor.
Okay, thank you very much for your kind introduction. And it's my honor to be here, and definitely honored to present a lecture for hydrogen production, especially today. And my name is Chang Won-yoon, and I'm a professor of chemical engineering at Postech. Let me share my presentation slide for today. Okay, there's some problem here.
Okay.
Can you see that?
We can see. Yes, we can see that
okay.
one.
Yeah, eventually we got. Okay, let me start with my lecture. The special lecture part 1 is the hydrogen production. So okay, let me start with the hydrogen economy. As you know already, the hydrogen economy consists of hydrogen production part, hydrogen storage, and hydrogen utilization. So what we are doing right now for hydrogen storage, okay, let me point option, laser pointer. Here, the hydrogen production part, the current technology include the natural gas fossil fuel reforming, the FF stands for fossil fuel. So natural gas fossil fuel reforming, steam reforming process, or we can use coal, petroleum, these things, this kind of fossil fuel. And we use this thermolysis, gasification technology and so forth to produce hydrogen. This is what we are doing currently. But in the future, especially in the near future, we need to use renewable energy, especially the wind and solar, to split water to produce hydrogen. Or we may use nuclear power plant waste heat in conjunction with the thermochemical cycle or high temperature electrolysis to produce hydrogen. This is what we want to do. Then the produced hydrogen will be stored using different hydrogen storage technology. Currently, we use the physical hydrogen storage, including the compressed hydrogen storage tank and the liquefaction hydrogen storage technology. But maybe in the future, the chemical hydrogen storage technology will be promising. This is because the chemical hydrogen storage can store a large amount of hydrogen in one time, and we can economically feasibly transport the hydrogen. And ultimately, the delivered hydrogen will be in conjunction with the fuel cells to produce electricity. Or we can use this hydrogen in conjunction with hydrogen combustion engine to produce power. This is what we want to do. So today, especially I will introduce you for hydrogen production technology today, okay? The question is that how we can produce hydrogen. So that's what I'm introduce you to, especially 3 parts. The first part is the fossil fuel reforming, and second part is the chemical dehydration, and the third part is the future technology and the water electrolysis. Okay, let me first start with the current hydrogen production technology. There are some sort of fossil fuel reforming processes here. The first process is steam reforming, is SR, and the partial oxidation, which is called this a POX. So it's a P here and the OX here. And the third one is the autothermal reforming process of fossil fuel. And the fourth is the dry reforming and others. So what's the advantages for this fossil fuel reforming process? First, it is economical. This is because previously, many companies, but industrial partners invest significant money to construct this kind of plant for hydrogen production utilizing fossil fuel. So this is why this is economical right now. So we can use the existing infrastructure, something like this. But the disadvantages include the fossil fuel reforming process release significant quantities of CO2. So it is absolutely needed to capture CO2 and sequestrate the CO2 in somewhere. That's the problem. Okay, I will skip that. So let me, but nonetheless, this fossil fuel hydrogen production technologies based on this fossil fuel nowadays, this is the major hydrogen production technologies. So we definitely need to know how it goes. So let me first start with the steam methane reforming process. So you can use the methane as a major constituent of natural gas. So I will So I'm not talking about the steam reforming of fossil fuel. I was talking about the steam reforming of methane. This is called this SMR. So generally, if we use fossil fuel here, and the steam reforming process means is we add steam here, and in the presence of a catalyst, we crack the CH and CC bond here to produce the CO and H2 here. Okay, that's the basic stoichiometric reaction of fossil fuel steam reforming process. But yeah, let me use this methane for steam reforming process. Again, the methane reacts with steam to produce CO plus hydrogen. So that reaction is endothermic. The reaction enthalpy here is a 260 kilojoule per mole energy. So if you can use this, the product gases here, and this is the mixed gas with the CO and hydrogen. This is called this synthetic gas, and hydrogen and CO ratio will be 3. But now we are talking about the hydrogen production technology, and if we use this produced hydrogen, will be in conjunction with, for example, the polymer electrolyte membrane fuel cell, is a PEM fuel cell, things like that, then we can't actually use this syngas for the to power the PEMFC. This is because the CO can poison platinum catalyst in a fuel cell. So definitely we need to remove this CO here. So what we can do is the CO removal technology here. So one of them is called this water gas shift reaction. So WGS reactions here. So what it does is the CO react with additional steam here to shift to the CO2 and H2 products. So you can imagine the oxygen here is transferred into CO to produce CO2 here. So steam is a reductant, right? So steam is the oxidant actually here, oxidant. So this reaction is ectothermic. It's about 41.2 kilojoule per mole here. So if you're thinking about the overall reaction, so you add a steam reforming and water gas shift reaction here, the CO is canceled out. So 1 CH4 and 2 moles of steam to produce CO2 plus 4H2 here. So the reaction enthalpy will be the 206 minus 41 to produce the 165 kilojoule per moles of endothermic reaction. So the total reaction energy is endothermic. So we definitely need heat sources to drive the endothermic reaction. But this process can be very efficient because we can do some thermal management here. And again, the hydrogen and CO ratio will be 3, which is high. Okay, so that's the reactor for steam methane reforming reaction. The steam reforming reactor shown here, and some catalysts actually equipped inside of the reactor, the radiation burner and heat transfer here. And if you look at the feed, here is about methane 25% with the 75% of steam, and it goes and produce the hydrogen, CO, and CO2, and unreacted methane, and some of the steams, things like that. Okay. And I will skip this. So this is the real case. If you look at the reactor for steam methane reforming, SMR reaction here. So here, so that's the cracking reactor, and the natural gas and steam goes in, and the reaction conditions shown here, this is a 20 and 30 ADM. It's a high pressure, it's a pressurized reactor, and the temperature is about 800 to 900 degrees Celsius. It's a very high pressure and very high temperature reaction. And the reaction happened to produce CO, the mixture of CO and H2. And I said we need to remove the CO. So here is the water gas shift reaction. The shift reactor means it's the water gas shift reaction, WGS reaction. And as you can see here, it's a two processes for WGS. The first one is the high temperature water gas shift reaction. We use high temperature water shift gas reaction to decrease the concentration of CO level into some sort of a lower level. Then we apply the second process which is called the low temperature shift water gas shift reaction to further decrease the CO level. So here, the HTS means it's a high temperature shift reaction is occurs at 350 degrees Celsius, and the low temperature shift reactor occurs at 200 to 100 degrees Celsius. And the rest of them hopefully will be H2, mostly H2 and CO2, and unreacted, still remain the CO here. And then the CO2 will be removed by the pressure swing adsorption technology or hydrogen separation membrane, and the remaining CO will further be removed by other technology here. So ultimately we can get the high purity hydrogen. Okay, and the second process for methane, second hydrogen production technology using methane is the POX. If you look at the complete oxidation of methane here, the 1 mole of methane react with 2 moles of oxygen to produce CO2 and steam water here. That is the ectothermic reaction. It's a very large ectothermic heat will be produced, so we can use it. Right? This is what internal combustion engine does actually. Okay, the POX is partial oxidation. So for complete oxidation, we need 2 moles of oxygen, but the POX for POX, we only apply 0.5 moles of oxygen here. Then we can produce syngas. The syngas ratio, the H2 and CO ratio is 2:1 here. Then what we need to do is to remove CO, right? Using some other water gas reactions force. So as you can see here, the total reaction enthalpy is the ectothermic. So in many cases, we do not need heat sources, right? So it's just burned. But the total heat in and out is low, so relatively low efficiency. But we can proceed with a very easy startup. And third method for hydrogen production is methane autothermal reforming process. And this process involves the first steam reforming process and second partial oxidation process. Again, the steam reforming process look like this, and the endothermicity is 260 kilojoules per mole, and the POX is a slightly ectothermic process. What autothermal reforming process is a kind of a combination of the steam reforming and partial oxidation. So if you add 2 stoichiometric reactions to methane and react with 1 moles of steam and 0.5 moles of oxygen to produce 2 moles of CO and 5 moles of H2. And total reaction heat will be 206 minus 36. That's 170 kilojoules per mole. So what it does is, what the concept here is, initially, if you add all these mixtures here, all this feed here, what it does first is the POX will be happen because it's easy, right? It's a very easy reaction, easy startup. It's an ectothermic reaction. So it immediately react with each other to produce syngas with heat. The concept here is to initiate the POX, then the produced heat will be utilized for triggering a steam reforming process. So relatively, because of this reason, this process is a relatively easy startup and high efficiency. So if you look at the autothermal reforming process here, So okay, this is the reactor, and this methane. The feed consists of the methane, oxygen, and steam here. And if you look at the temperature profile, so first, when this feed goes in, that's the reaction path here. So what's the initial process going on? I'm saying the POX will be occur. So the POX produce heat. So if you look at the temperature profile here, the first path of the reforming reactor, the temperature will be rise up. Up here is about 1000 degrees Celsius. Then the next reaction will be next reaction will be steam reforming process, which need to absorb heat because it's endothermic reaction, and the produced heat will be absorbed by steam reforming process, and in certain point the temperature will be stabilized and the maintained. So this is why this is called the autothermal reforming process. And the rest of the feed here, off gas include the hydrogen, it's about 30 volume percent, and CO2 10, CO unreacted methane, and steam and force. So after passing through this reactor, this mixed gas need to be purified to obtain high purity hydrogen. Okay, so that table shows you the comparison for hydrogen production using, for example, the methane here. So 3 representative processes for hydrogen production: steam reforming, and POX, and autothermal reforming. If you look at the additive here, for steam reforming, steam will be added, and the POX is oxygen, actually it's air will be added, and autothermal reforming is add steam, both steam and oxygen. And startup here, this is slow. This is the big reactor, and the temperature is about 800 and 900. So it takes time to increase the reaction temperature. So startup slow. The POX is so fast, and autothermal reforming is a kind of middle. The reaction size, the steam reforming process, the reaction size is big. POX will be small, and autothermal reforming process is just about, in between. The hydrogen concentration after the reaction, steam reforming process is 3. So if you remember the H2 and CO ratio, the steam reforming process is 3, and POX is low. It's about 1 and 2 something, 2, right? The autothermal reforming is 2.5. Okay, so that slide shows you the steam to carbon ratio versus the oxygen ratio. So if you look at this is the oxygen, the x-axis represents the added oxygen. The 0 means is that no oxygen is added. So the steam reforming process react with the methane plus steam. So that SR process will be positioned here. And the added steam and carbon ratio will be in the range of 2 to 10. And up to here, if you add more oxygen and oxygen here, and you can go to the POX region, but the y-axis is 0, which means no steam will be added in this region, right? So that's the POX region, and the added oxygen range will be 0.2, between 0.2 and 0.6, something like that. And the ATR is in between here. And if you add axis oxygen, then you can go to not the process for syngas production. Your reaction will go to the combustion range. And so this produced hydrogen will be supplied to fuel cells. So let me briefly introduce some fuel cell technology very briefly. So there are there are many types of fuel cells here. The first fuel cell is the PMFC, the PEMFC. The PMFC stands for polymer electrolyte membrane fuel cell. or PAFC stands for phosphoric acid fuel cell. That's the thing. And the MCFC stands for molten carbonate fuel cell. So here's the CO3 2 minus here. And SOFC stands for solid oxide fuel cell. So it actually means it's the electrolyte will be solid oxide. If the electrolyte is solid oxide, we call this SOFC, solid oxide fuel cell. The electrolyte is molten carbonate, then we can say molten carbonate fuel cell. And the electrolyte is a polymer, then PMFC, or the electrolyte is a phosphoric acid, a concentrated phosphoric acid here, then you can call it, it's a PAFC here. So if you look at the first PMFC here, and what it does is actually all fuel cells actually consist of membrane, electrolyte in between, and two electrodes here. So one is anode, and another is cathode. So the fuel goes in here in the, for example, the PMFC. In this case, the fuel is H2, right? So what it does first is this H2 will be decomposed into 2H plus 2 electrons here. And the H plus will then be transferred through this membrane here. And the H plus, the proton will be passing through the membrane to get the cathode here. And the electrons, the separated electrons, passing through this electrical current and working here, so produce power, work, then the electron goes in. And the transferred proton will react with electrons and oxygen. Here the oxygen goes in, then produce water. That's how it works. And it works, right? So that's how fuel cell work here. And the molten carbonate fuel cell, in the case of molten carbonate fuel cell, the electrolyte is a carbonate here. And okay, for example, the fuel is a hydrogen here. The hydrogen goes in and separated, and electron goes, and the other side oxygen going on. But in this case, it's a cathode. At the cathode, the O2 and actually CO2 also goes in here in the cathode side, and the O2, CO2, and electrons reacted with each other to produce carbonate, molten carbonate, and the molten carbonate going through the membrane to reach anode. At this anode, it decomposes CO2 and the water, and it goes up. And the CO2 reused to supply to the cathode, and this process is repeated. And the electron passing through here and work. And the solid oxide fuel cells, actually solid oxide is a O2 minus conductor. So charge carrier is the O2 minus ion. Here is the charge carrier is H plus the proton, right? So in this particular case of solid oxide fuel cell, it's the O2 minus is the conductor. So what it does is here, the air, the oxygen actually here and reacted with electrons to produce O2 minus. And the O2 minus passed through the electrolyte and reach anode, and that O2 minus react with hydrogen to produce water and electrons. The electrons going through this line and repeat this process. So if you look at here, so this is the solid oxide here, and the charge carrier is O2 minus, and the O2 minus must travel from cathode to anode, must transfer here to here. So which means is because it's a solid, right? The rate of the oxygen 2 minus conduction will be very slow at low temperatures. So generally in solid oxide fuel cells, the fuel cell operation temperature will be 800, over 800 degrees Celsius. Nowadays, it's about 750, and sometimes 700 degrees Celsius. Anyway, it's a very high. And this is the carbonate is the charge carrier, right? But carbonate itself is a solid. So this is why we need to make a molten carbonate, so we can make an easy transfer of this heavy charge carrier from cathode to anode. So this kind of molten carbonate fuel cells, the fuel cell operating temperature will be is about 600 degrees Celsius to 650 degrees Celsius, something like that. And in the case of PMFC, yeah, it's a protoconductor, it's a polymer, and the protoconduction is very easy at relatively low temperature. So generally, in the case of PMFC, the operation fuel cell temperature will be lower than 200 degrees Celsius, generally 120 degrees Celsius, something like that. Okay, and how we can connect with the produced hydrogen with this fuel cell. So that slide shows you that connection. So let me continue to talk about the fuel limitation for fuel cell. Not all the fuels are appropriate for fuel cell. Some fuels are really not appropriate for fuel cell. So if you okay, here is a lot of 5 kinds of fuel cells here, but let me focusing on just PMFC and MCFC and SFC here. And let's say, okay, imagine fuel is a hydrogen, and hydrogen go for PMFC, then that's fine. Hydrogen is a fuel, and hydrogen go for MCFC, that's fine. Hydrogen is a fuel here. And hydrogen is also fuel, efficient fuel for solid oxide fuel cell. Well, let me talk about the CO. In the case of CO, right, CO can't really be an appropriate fuel for PMFC because, again, the PMFC, the electrode here, okay, here the electrode materials is a platinum. Actually, platinum is located at this anode here. And if CO goes in, and the CO strongly bind with the platinum to deactivate the whole process. So CO must be removed for PMFC. Okay, this is CO is a poison, not fuel. So here is over 10 ppm, then it poison PMFC. But nowadays we say less than 1 ppm of carbon monoxide CO must be supplied into PMFC. But interestingly, for these kind of high temperature fuel cells, right? This is over 700 degrees Celsius. This is 650 degrees Celsius operation temperature. This kind of high temperature fuel cells, CO is a fuel. This is different because the reaction temperatures are very high. Even here, generally nickel catalyst actually used for electrode, but CO can also bind to nickel, but because of this high reaction temperature, the bound nickel can be relatively easily take off from the nickel side. So it so see this because of this region, CO can be a fuel for this. And how about sulfur? In the case, why we are talking about sulfur? Because the natural gas contains a lot of sulfur. So we need to know what's the effect for the sulfur for fuel cell operation. But in the case of a PMFC, there is no significant studies on effect of sulfur on operating PMFC. So we don't know exactly. But in the case of MCFC and SOFC, the high temperature fuel cells, actually the sulfur cannot be used for these fuel cells because here again, the electrode material is a nickel. If the sulfur supplied into these high temperature fuel cells and sulfur react with nickel to produce nickel sulfide species to deactivate the whole process. So the lesson here is the PMFC we need to remove CO for high temperature fuel cells, including MCFC and SFC. It is absolutely necessary to remove S species here. Then you can imagine, right? For example, for steam reforming process, actually, okay, that steam reforming process of methane proceed to produce this syngas, then you can directly supply this mixed gas into high temperature fuel cells here. Right here, there's no problem because the hydrogen is the fuel, the CO is the fuel, right? But cannot be supplied into PEMFC because CO can poison the PEMFC here. So that's the difference. So then anyway, then what is the technology for CO removal for utilizing PMFC here? So the first one is, for example, the water gas shift reaction. That's I already discussed. And another CO removal technology is the PROX, which stands for preferential CO oxidation. So here is the POX, it's a PROX, or the methanation reaction and the membrane separation. This is usually the palladium membrane to purify hydrogen. And the other thing is the pressure swing adsorption reaction. This which is called the PSA and commercialized technology. And how about what's the sulfur species removal technology? This is called a hydro desulfurization technology, which is called HDS. So fossil fuel. So we need to remove organic sulfur species less than 0.1 ppm. The first step is the hydrogenalysis. This means it's add hydrogen, right? Add hydrogen. Lysis means it's a cleave. So add hydrogen to cleave, right? So again, this process here, for example, the organic species react with hydrogen, then it produces ethane. It's a diethyl sulfur, ethane, and H2S. The catalyst involved in this process is nickel molybdenum oxide, supported on alumina. Generally, people call this a NEMO catalyst, or the cobalt molybdenum oxide supported on alumina. This is called COMO. So the reaction temperature is 300 to 400 degrees Celsius. And the second step is to produce H2S, then further react with zinc oxide. And the zinc, like sulfur, more than the oxygen here. So some sort of exchange reaction happen and produce H2O and zinc sulfide. That's how it does actually. Then let me talk about the fuel conversion system. Fuel conversion system means sometimes the people call this a fuel processor or fuel conversion system or hydrogen production system for fuel cells. Here, applied for a PMFC system. For example, let's say we can use natural gas as a fuel here. And what first step is desulfurizer, right? So remove sulfur here, and the steam, add steam, and as a steam reforming process going on at 800 degrees Celsius, and produce the gas. Produced gases will be the syngas, CO plus H2. Then we further add steam to convert the CO to CO2, right? So 2 steps for water gas shift reaction. That's the actual ingredient. That means it's high temperature shift, low temperature shift. And then the still remained very low concentration of CO can be further removed by PROX, the preferential oxidation, after adding hydrogen. Then we can produce hydrogen-rich gas, including less than 1 ppm CO here. And if you gasoline is a fuel for PEM fuel cell, so what it does here is just add steam and air, which means is that you can proceed autothermal reforming reaction, which is occurred at 800 degrees Celsius. And here the zinc oxide. Why we use zinc oxide? Because we want to remove the sulfur species, right? So add using proceed ATR reactions and remove sulfur. And then here the gases here at this stage will be the mixture of CO and H2. Then WGS reaction will occur to further remove CO. Then finally remove additional CO level less than 1 ppm to produce hydrogen. That's how it works. And this is the real system. I'm going to skip that. And I'm going to skip that too. But in the case of SOFC system, solid oxide fuel cell system, the hydrogen processor will be much simplified. For example, the fuels goes in, and the catalytic reformer cracking, and reformed gas is directly supplied to solid oxide fuel cells to produce power. That's much simpler. And here's an example for a methanol reformer. This is actually applied for submarine. So this is a proven technology. This is German company, it's a HDB submarines. Actually, they use methanol as a fuel to power PMFC here. So generally, the proven technology used the metal hydride as a hydrogen storage. I'm not going to deal with this hydrogen storage today, but here's a metal hydride here. And then to produce hydrogen, just stored using metal hydride and goes in. And if we need hydrogen and add heat here and we produce hydrogen to supply fuel cells to give electricity. That's how it goes for now. This is proven technology, but now we are doing some developing methanol reformer system for submarine. And this is the methanol reformer, right? So reforming reaction, methanol, steam goes in, and after reformed, the gas purification means is some sort of WGS or other reactor here, and produce hydrogen will be supplied for fuel cell, and the remaining gas provide as a fuel to supply the sufficient heat for this reforming reactor. Okay, the next process for hydrogen production is the dry reforming of methane. So yeah, I talked about the steam reforming process. Here is the we use steam as an oxidant, right? And go here. But the dry reforming process, we actually use CO2 here to produce syngas, right? This is the difference. The methane react with steam, but here is a methane steam react with CO2 to produce syngas. So if you look at the reaction energy, this is even more endothermic compared with this steam reforming process. But why we want to use this? Sometimes, this is the 1 kilowatt scale class, the SOFC stacks here. This is the fuel cell stack. And that as these SOFC stacks react, so just continuously producing electricity from this SOFC, the heat actually will be developed here. Then that causes problem. This overheating actually, break down this whole stack. As you can see, it's a continuously break down this stack. So and totally deactivated. That's the problem. So one of the issues here when we use SOFC stack, utilizing hydrogen, then how we can cooling down this overheat? That was the problem. But one of the idea is we may use in conjunction with this high endothermic steam methane process, for example, okay, so not providing hydrogen directly. We just use the natural gas with steam here. Then what will be going on here is the SMR, steam methane reforming process will be going on, right? And real-time process the syngas, and the syngas, supplied into these fuel cells to give electricity. But at the same time, as this reaction proceed, that actually need heat, right? This is a high endothermic reaction. And as this reaction proceed, that reaction absorb this heat to cooling down this SOFC. That's the idea. So that actually is going on. And we can use here is SMR or the dry reforming process, because even the cooling effect will be higher. So that's how it goes. So I'm not going to talk about this. Yeah. Okay. So that's how it goes. That's how we can produce this, use these types of dry reforming process. Okay. But another issue still exists. One of the issues is compared with the steam reforming and dry reforming reaction. If you look at the reactant, in the case of dry reforming, that reaction contains more carbon. So one of the issue can be happen, for example, the catalyst deactivation, because the dry reforming reaction goes on. These carbons, upon breaking this CH, CC, and CO bond here, the produced carbon actually deposit at the surface of this electrode catalyst electrode, and deactivate. That's the problem. Another problem is, okay, this deposited carbon produce some sort of this carbon filament, because the nickel catalyst can make it. Actually, this is a catalyst for produce carbon nanotube or things like that. So this kind of carbon filament produced, then that carbon filament will break down this nickel electrode. That's the problem. So rapid deactivation of the cell will happen. And another problem is the nickel sintering. Nickel sintering means it's a nickel aggregation at high temperature. And for the first time, before the reaction, the nickel species is well dispersed at the support. But after the reaction is going on at high temperatures, this nickel, diffuse, the surface diffusion of this nickel happen, and nickel react with, this to produce this nickel aggregate to deactivate species. So we need to develop relevant technologies to prevent this kind of catalyst deactivation. So a lot of catalysts are developed in this regard. Here is a nickel with some cobalt as a co-catalyst supported on alumina, and nickel here the cobalt, and some sort of ruthenium and platinum. So precious metal catalyst can be also used for these. Yeah, I'm not gonna use this. Okay, let me just briefly. So this dry reforming of methane process, this kind of catalyst development is very important, is what I say. Another important parameter to optimize the dry reforming of methane reaction is operating condition. So actually we supply the mixture of methane, steam, and oxygen here, and some, depending on the ratio of the added methane, water, oxygen, in some sort of region will derive carbon formation. So that this we can't actually use the composition of this methane, steam, oxygen with this in this range. And carbon-free region is good. Generally, if you want to go from this carbon formation to carbon-free region, what you can do is you can use more oxygen species. For example, more oxygen here or more steam here. Then you can prevent the carbon formation because the formed carbon can react with O2 and steam to produce CO and CO2 to remove it from the surface. But in this region, the problem is if you use more steam and more oxygen, especially more steam here, then you require like more energy, more input energy will be required. So that's not the really optimal region. So here is the optimal region here, some sort of this composition range. So this is why the operating conditions are very important. But in the case of dry reforming reaction, actually the same. The methane, CO2, for example, CO2. If you think about the CO2 here, and there is an optimal condition regions to drive the dry reforming of methane without catalyst deactivation. So it is important to know. It is important to understand. So what kind of operating conditions are really needed for durable operation of fuel cells. Okay, up to here, I discussed about some other current technologies for hydrogen production, particularly based on fossil fuel. Okay, in summary, briefly, and the fossil fuel hydrogen production technologies are very useful to produce mass quantities of hydrogen, and the produced hydrogen can be in conjunction with fuel cells and or hydrogen turbine to produce electricity. For fossil fuel, for example, the methane-based hydrogen production technology, I mean the natural gas-based hydrogen production technologies, I talked about the steam methane reforming process, which is called SMR, and then talked about the POX, the partial oxidation of methane, and the third one is the autothermal reaction of methane, and the fourth one is the dry reforming of methane. All these kind of different technologies can produce hydrogen, especially first it produces syngas. Syngas contains the H2 and CO, but these gases, if we want to use these gases for especially pure fuel cells, then we need to remove sulfur or the CO, carbon monoxide. So we discussed about the CO removal technologies, including WGS, water gas shift reaction, and POX, preferential oxidation, or the PSA, pressure swing adsorption, or hydrogen separation membrane, and so forth. And for sulfur species removal technologies, we talked about the HDS process, right, involving nickel molybdenum or cobalt molybdenum catalyst and zinc sulfide catalyst and so forth. Okay, but yeah, up to here is the fossil fuel based hydrogen technology. And from now, I'm gonna talk about the recent research for hydrogen production, next level of hydrogen production technology. What we want to do, actually, what we want to use is to use the renewable energy. That's the really big things for realizing carbon neutrality. That's zero, right? So especially solar and wind is the one of the resources for this hydrogen renewable energy. And the thing should be using renewable energy, electricity, and that will be the electricity is supplied into electrolyzer and split water. So water electrolysis. Electrolysis means electron, add electron, provide electron. Lysis means it's a cleave, right? Hydrolysis means add water, and cleave bond. So electrolysis means is add electron. Electron means add electricity and cleave wedge bond here to produce water. That's what we want to do, really. And so I'm gonna a little bit talk about this water electrolysis. And other hydrogen production technologies include the thermochemical cycle and photoelectrolysis and biological hydrogen production technology. I'm going to very briefly mention about these new technologies for hydrogen production. Okay, first let me talk about the electrolysis. Electrolysis is the exact inverse operation of fuel cells. So if you look at the left side of the slide, that shows you the fuel cell operation concept. Here, the membrane here, and two electrodes. Okay, the membrane is a polymer. Then we call this a PMFC, right? The membrane is molten carbonate. Then we called molten carbonate fuel cells, MCFC. If the membrane is a solid oxide, then we call this a solid oxide fuel cell. And anode here and cathode here. So two electrodes here anyway. And fuel, such as hydrogen, will be supplied in the anode, and oxygen from air, actually air supplied into cathode, and the electrochemical reactions happen. Then the outcome will be electricity and water. That's the fuel cell, right? The electrolyzer is the exactly inverse operation. So what it does is, if we add electricity, here is the out is the electricity and water. So in here is the electricity in, the water in, and what's the out? What's the out is one side from hydrogen will be produced from one electrode, and another electrode will produce oxygen. That's how that's what electrolyzer does actually. If hydrogen and oxygen is not separately produced, then it will proceed the combustion reaction, right? H2 react to. So if you imagine, okay, this electrode produce hydrogen and oxygen, and what's going on? What will be going on? Will be the combustion reaction happen, and it's a boom, right? So it must be separated. The hydrogen production part and oxygen production part should be separated, right? So this is why why membrane is actually here. Okay, so that's the fuel cell. That's the electrolyzer. It's actually the fuel cell and electrolyzer is the same. Okay, but the difference is, okay, this is the fuel cell. Hydrogen goes in, oxygen goes in, electrochemical reaction happen to produce water and electricity. And the reverse reaction happened, then that turns to electrolyzer. So we give electricity and provide water here, and one side produce hydrogen, the other side, another side produce oxygen. And yeah, actually the first order electrolysis was, developed even 1800, the year of 1800 is made. Right? It's a long time ago. Here is William Nicholson and Anthony Callisto discovered a chemical reaction by electricity. Right? This is the Royal Society of Chemistry, and it's a platinum catalyst here. Yeah, so I'm going to skip that. And like fuel cells, there are a type of electrolyzers. So you can imagine if the separation, the membrane, if the membrane, separation membrane, separation electrolyte is a polymer, then we call this a PM electrolyzer, PM electrolysis, polymer electrolyte membrane electrolyzer. If the separation membrane will be solid oxide, then what is called? Yeah, you can imagine, right? Solid oxide electrolyzer here. And if the electrolyte is alkaline, such as the potassium hydroxide, then which is called this alkaline electrolysis. So let me just give me an example. If you look at the PEM electrolyzer here, okay, let's say the anode reaction, the water goes in, and that separate oxygen. Water goes in, and oxygen produced, and separated proton and electron, and proton passing through the membrane here, and electron passing through here, and here recombination of electrons. Here the transport of proton to produce hydrogen. That's how it works. And among three technologies, the alkaline electrolysis is commercialized already. And so nowadays, many companies actually utilize this commercial alkaline electrolysis to produce mass quantities of hydrogen for net zero. And the next technology is the PEM electrolyzer. But PEM electrolyzer has an issue. One of the issues for this PEM electrolyzer for mass production of hydrogen, here actually the iridium catalyst actually is used in the PEM electrolyzer. But as you may know, the iridium metal is so expensive. So that's the problem. So if we can't actually replace this iridium catalyst into a more cheaper metals, then it may not be able to use this PEM electrolyzer for mass quantities of hydrogen. And a little bit more next generation technologies is the solid oxide electrolyzer. Generally, people call it SOEC, solid oxide electrochemical cell, SOEC. So this is, my lab, actually, we involved the development of SOEC technology. So as you see, the electrolyzer, so give electricity and water split the hydrogen and water. Why the volume produced volume is different? Because water split water to produce 2 moles of hydrogen. Two moles of hydrogen will produce 2 moles of H2 and 1 moles of O2. Okay, yeah. So that's the comparison for different electrolyzer here. For operation temperature, the alkaline electrolysis is operated in the range of 40 and 90 degrees Celsius. And the ion transferred will be OH minus. So they generally use alkaline solutions such as potassium hydroxide. So the OH minus transferred will be involved here. And the PEM electrolysis is operated at the range of 20 means is the room temperature to 100 degrees Celsius. The charge carrier here is H plus, right? And the solid oxide electrolysis is SOEC. It's like SOFC. The operating temperature is very high. It's over 700,000. And the ion transfer will be the O2 minus. And you can just see a further additional comparison. For example, here, the electrode materials for alkaline reaction is iron, nickel, cobalt, all cheap. So there is no issue for catalyst cost. But in the case of PEM electrolyzer, precious metals are used, especially iridium and platinum. That's one of the issues, especially iridium is the issue. Solid oxide electrolyzer is a nickel containing ceramics, so there is no issues on catalyst cost. And temperature range I talked, and the pressure, the alkaline fuel cell is generally operated less than 30 bar, and the PMF is can be operated up to 200 or 300 bar, and the solid oxide electrolyzer operated near the atmospheric pressure. Now the capacity will be up to 3.2 here, 380 normal cubic meter per hour case. The PMFC is much smaller than that, and solid oxide electrolyzer is much smaller than that. But there is a, here, the alkaline fuel cell, alkaline electrolyzer, I said it's commercialized and look like this. So MAC5, actually, this is the cell. And here you see that's the actually cell. So each cell stacked together to produce high capacity water electrolyzer. So Nel Norway is a Norway company. Nel is one of the leading companies for this alkaline electrolyzer. Here, the lifetime for alkaline electrolyzer is near 10 years. And the PM electrolyzer also, you can even buy, the PM electrolyzer is a megawatt scale, but there are still a lot of issues to commercialize for that, iridium and some other durability. But here is some of the company claim that the durability of the PEM electrolyzer can reach to 7 years, but it's still need to be approved. And yeah, this is also PM electrolyzer here. So you can each stack is a 15 normal cubic meter per hour. So it's a 1, 2, 3, 4. So this system produced the 16 normal cubic meter per hour hydrogen production capacity. Yeah. That slide just show you the water splitting. Actually, the gift-free energy is positive, means it's not spontaneous. So that reaction actually require really large energy. So definitely we need to use renewable energy to triggering this water splitting reaction. Otherwise, if you think about, okay, we can use electricity produced from fossil fuel, then what's the point for produce hydrogen for water, right? That's the thing. And yeah, I'm gonna stay. I'm not gonna going through the detail here. And yeah, I think I can skip here. Yeah, I can skip. Okay, that up to here is the water electrolysis. Let me just go for the next hydrogen production technologies. The next hydrogen production technologies is thermochemical cycles. The concept here is usually here it's a direct thermolysis. Thermolysis means it's add heat, right? Heat lysis is break the bond. So direct thermolysis of water. So if you just heat the water to split water, then generally the required temperature will be 4,300 Kelvin. It's about 4,000 degrees Celsius. This is too high, right? It's too energy intensive. The concept here is by multi-step thermochemical processes, the temperature can be reduced to it's about 1,000 degrees Celsius. So 1,300 Kelvin, something like that. The concept here is, okay, we can use MO, for example, it's a mediate, and that decomposed to produce M plus O2, right? And then M react with water and take oxygen here to produce hydrogen. So we can repeat this process. If you look at this here, the water comes in, and first oxidation of M. So M react with water and take this oxygen to produce H2 here. And this oxidized MO, will be reduced to produce oxygen, right? Using some external energy. Definitely, we need external energy. I said it requires about 1,000 degrees Celsius. And that external energy sources will be the solar thermal or some other nuclear power, the excess thermal energy from nuclear power plant as forth. That's the thing. So one of the real example for is the iron redox cycle. So we can use the redox cycle of iron. And this is developed by the Sandia National Laboratory in the United States. So here's the thing. So M is FeO here. So this is 2. The oxidation state is 2, right? So the FeO iron oxide first react with water to produce hydrogen, and the oxidized form of iron species is Fe3O4. So if you're thinking about the oxidation state over here, is oxidized, and then Fe3O4 decomposed to produce oxygen and FeO back. Then we can repeat this cycle to produce hydrogen. This is the concept. And yeah, this is the similar thing. So I can skip. So that's the just water splitting based on this the thermochemical cycle in conjunction with nuclear power plant energy. Yeah, I'm going. Yeah, the next thing is the photoelectrolysis. Photoelectrolysis means it's to add photon and electrons and split water, right? So here's the concept. If we use some sort of semiconducting materials having this valence band and conduction band, and so in this particular in this semiconducting materials, there is a band gap here. Band gap means it's a gap between the valence band. Valence band is the filled electrons, and the conduction band is an unoccupied band, right? That what will be happening here is you can absorb a photon here, which is in resonance with this band gap energy. Then what should be happening is that add the photon, and one of the electron can be excited and into the conduction band here. Then here is negatively charged electron generated here in the conduction band, and hole will be generated in the valence band. And we can use hole for water oxidation to produce oxygen. And we can use these electrons to water reduction to produce hydrogen. That's the concept. So this concept, was developed very, it's very previously here, but it's not really commercialized yet. So one of the things is, how we can use a broad range of sunlight for electron production. That's the one thing. So people actually focus on the materials for this purpose. But here, this is Jack's paper, the 2010. It's about 13 years ago, but still, in 2010, the Jack's paper says that none has so far been found with the needed efficiencies, cost, and stabilities for a practical deployable system. But here now, in 2023, people do R&D, research and development, for over 10 years more, but still there's no actually system for a practical and deployable system. So if you're interested in this area, you need to study previous volume of literatures and how I can design the relevant materials for this purpose. Okay, so I'm not gonna going through. And the last production technologies is the biological production. So this biological hydrogen production include the direct biophotolysis, is using biomaterials and photon to split water, and the indirect biophotolysis and some fermentation technology and some fluors. So I'm not really talking about the detail here. Just so you can see there is a biological hydrogen production processes for hydrogen. Okay. Yeah. I think that's what I'm prepared for today. So today the final summary is I talked about the hydrogen production technologies based on fossil fuel in the first section. Then next section, very briefly, I introduce you some other recent technologies for hydrogen production, especially water split water. Okay, so hope this lecture help you to have some relevant knowledge to you. So thank you very much for your attention. And if you have any questions, please let me know. And you can contact me directly by email. If you do not have questions right now, then you can just directly contact me. Okay, thank you very much again. Okay, I'm done. The connection.
Hello.
Yes, I can. I'm here.
Okay. Yes, Professor. Thank you very much for the nice talks for the lecture for the hydrogen energy, because it is related with our class from hydrogen energy. So we talk about the methane reforming, something like that. So maybe we will continue to the question and answer session, Professor Yun, if you don't mind.
Okay, yeah, definitely. Yeah, sure.
Yes. So if someone from the class, I will turn on the camera for in the class. So if someone from the class will have the question from for Dr. Yun, for Professor Yun here related about this hydrogen energy and something maybe you are interested about the research about the SOEC, solid oxide electrolysis cell, something like that, you can ask Dr. Yun directly. Okay, siapa yang mau tanya, tunjuk tangan atau raise hand di Zoom-nya ya? Okay, we have Ar-Rashid Farhanda Putra, Professor Yun. Silakan Rashid.
Oke, thanks for terima kasih untuk kesempatannya Pak Ridwan. And I'm Rashid. I'm student from batch 2019, and I'm a part of Dr. Muhammad Ridwan research group. So I have a question. If I'm not making a mistake, I have read that Hyundai on 2015 are success developing hydrogen fuel cell car using PMFC, but until now it is not for commercial use. So my question is, what is the truly problem that car industry faces on developed hydrogen fuel cell car? So that's my question. Thank you.
So your question is the PMFC. Are you talking about the PMFC?
Yeah, PMFC on the car use.
Okay, that's a good question. So your question is, let me make sure. Your question is, there are a lot of effort on developing the PMFC, right? Especially which can be applied for hydrogen fuel cell car, right? But
yes,
it's not really commercialized so far.
Yes.
So why is that true then, right? Okay.
Okay.
Yeah. So that's a really good questions. And actually, some other companies are commercialized. Some company such as the Toyota and the Hyundai Motors. Actually, Toyota is a Japan company, and the Hyundai Motors is a Korean company. And they actually commercialized hydrogen fuel cell car. right? So actually, I'm preparing slide for this for the next lecture for hydrogen storage part actually, but they commercialized, but not significantly right now. As you said, one of the reason for this is the hydrogen fuel cell car equipped with the PMFC is fine. You can buy it if you want, but one of the problem for this is there is no sufficient amount of hydrogen refueling station. That was the problem. So because of this, the lack of infrastructure for hydrogen supply for hydrogen fuel cell electrical vehicle, so people, for the first time, people bought a car, but there is, it's very inconvenient. I can't really use that car for a daily purpose. So that was the problem, and people, slowly changes. The trend will be changes, and nowadays people, more and more like buy electrical car, right? Tesla, something like this. So I think technologically is fine, but what we need to do for the further commercialization of the PMFC is that the durability of the PMFC need to be more extended. Yeah, but currently it's 5 years, that's fine, but we should achieve it about over 10 years, something like this, right? So that's the one part. And the other part is still a lot of platinum catalysts are used in the PMFC. So we definitely need to put our effort to reduce the amount of platinum catalyst of the fuel cell. And third one is not really directly related to the technology on hydrogen fuel cell electrical vehicle, but the third one is the hydrogen supply infrastructures are constructed for wide use of the PEM fuel cell. Okay. That does answer to you?
Yes. Thanks for the answer. Thank you.
Yes. Okay. Thank you, Rashid, for the question, and also for Professor Yun for the answer. So maybe we can have like one more question for Professor Yun, or one or two questions. So someone in the Zoom can raise hand. Aman itu ya? Okay. Someone can raise hand. Okay, maybe from the class. Do we have any question for Professor Yun? Ada yang mau nanya dari kelas? Evan, Mario, yang lain? Farah, siapa? Oke. Nanya aja, nggak usah malu-malu. Nggak pakai bahasa Inggris yang biasa aja juga nggak apa-apa. Cuek-cuek. So raise hand ya. Okay. So who will ask? Please raise hand. I mean, they have question, Professor, but it seems like they don't have the
Okay, that's fine.
percaya diri apa sih? Kok saya lupa. The self confidence they have. They don't have the confidence to ask in English. So I will try
That's
to.
fine. That's fine. Okay, if you later, if you have any questions more later.
Good morning, Professor Yun.
Okay, nice to meet you.
Okay, my name is Mario. I'm quite interested in hydrogen production with biological process. I kind of confused. How can you quite explain it a bit about hydrogen production using a biological aspect, sir?
Okay.
For brief.
Thank you very much for your questions. And unfortunately, I'm not an expert on biology. So biological hydrogen production method, I can't really explain what's the real technologies for biological hydrogen production. What I know is, biologically hydrogen can be produced, and some other bacteria, some other bio material, I'm not sure it is right or not. So bacteria or microbial can, some act to produce hydrogen internally. But many researchers said for the commercial mass quantity of hydrogen production method, the biological method may not be directly applicable for that purpose. That's probably what I heard, and some scientists for biological hydrogen production. Scientists who conduct the biological hydrogen production method, actually they construct really big volumes of water tank and using some algae and some other bio stuffs here, and for a long time they produce hydrogen. So that's what I know. Okay, I'm not an expert of biological hydrogen production. I'm a catalyst guy. So I'm sorry for not a sufficient answer for these questions. Okay.
All right. Thank you, Professor Yun.
Thank you very much for your questions.
Thank you, Professor Yun. Yes, Professor Yun is an expert in heterogeneous catalysis, Professor Yun, right? So, maybe he knows about the biological hydrogen generation, but it's not that deep. He's an expert in the heterogeneous catalysis. Okay, one more question from the class. Or in the Zoom, if someone wants to ask Professor Yun regarding the hydrogen production. We have Hana Rufaidah. You can ask directly. Go ahead, Hana.
Halo. Halo. Yes. Professor Sang is clearly. Halo.
Hana suaranya nggak kejelas, nggak. I can't really hear. Listen to. It does, the sounds is I don't know. It's a technical problem, I think.
So Hana, can you maybe fix the speakerphone or something so we can hear you clearly. Okay, while waiting, we have also, I saw there's a, here in the participant, if you still remember, we have Safira Ramadhani. It looks like Dr. Son Hyuntae students also came here, Professor. If you
Really?
remember her,
Yeah, sure.
also join us. Okay, Hannah, maybe there's a problem with the speakerphone, Professor. So we have.
Okay.
So waiting for Hannah. Is there any question? Yes, you can ask. You can ask. You can chat. You can ask Professor Yun through chat. So I will read it for you.
I can see chat.
Okay, maybe because the time constraint. Okay, Professor, thanks for the opportunity. I'm Hana Rufaida. I wanna ask. We already know that there is a lot of method to produce hydrogen, such as with ammonia borane, hydrogen hydrate, and formic acid. What are the most feasible differences in the SMR method compared to other methods? Thank you, Professor. So probably what she's saying, that she's asking that we have steam methane reforming reaction, water gasification reaction, but compared using the ammonia borane, hydrogen hydrate, or formic acid, what is the feasible differences, Professor?
Yeah, that's a really good questions. Actually, I prepared. Yeah, I'm gonna deal with this subject in the next hydrogen storage section. Actually, so one of the visible differences compared with the SMR process is this kind of material, such as ammonia borane, hydrogen hydrate, formic acid. These kind of things are actually used for hydrogen storage materials. So which means it's okay. We can use methane. We can use methane as a hydrogen storage material, but the problem is in that case, so hydrogen storage materials means we produce hydrogen and store hydrogen, and we need to deliver this hydrogen into a desired site. And we can use methane, actually. So methane contains hydrogen, right? And methane delivery, methane transportation is well constructed, right? We can use the infrastructure, and at a desired site, we can decompose methane using SMR to produce hydrogen, but a lot of CO2 is coming out. That's the problem. One of the purposes for this is how we can reversibly store hydrogen and release hydrogen, hopefully not involving CO2 production, by production. So for this purpose, some specific examples of materials are developed. That's the ammonia borane. Ammonia borane was one of the promising candidate for transportation fuel. I mean, the hydrogen storage materials for transportation, hydrogen fuels electrical vehicle. But now the United States, the Department of Energy actually decided not to go with the ammonia borane. But anyway, but still ammonia borane is a good materials for this. And the hydrogen the same. The formic acid, actually the formic acid is a concept for formic acid is to use CO2 as a hydrogen storage medium. So use CO2 and CO2 hydrogen reacted with each other, produce formic acid and delivered. And on demand, you can decompose formic acid to produce hydrogen and CO2. Then people said, okay, because we use CO2 as a hydrogen storage medium, this formic acid can be CO2 neutral, something like this. So my answer is the visible difference is the SMR is a clearly hydrogen production technology. And this kind of technology involving ammonia borane, formic acid, and ammonia. And I'm going to talk about the liquid organic hydrogen carrier, LOHC, this kind of thing in the next lecture. This kind of things is designed for hydrogen storage materials. I'm going to explain that later, more detail. Okay.
Okay, thank you, Professor Yun, for the answer. So remember, we have the second session lecture regarding this other kind of hydrogen production, hydrogen storage, something like ammonia. What is one of the expertise of Professor Yun about ammonia, hydrogen production from ammonia, something like that, and ammonia borane and formic acid. There's specialties from Dr. Yun, at least when he was still in KISS. Now in the post-tech, maybe he's still doing that research. So Professor Yun, due to the time constraint, maybe we can wrap this first session of lecture, and we can have another lecture maybe in this week or the next week, Professor Yun. Maybe I will coordinate you again for the time.
Okay.
Yes.
Thank you very much for that.
Thank you very much, Professor Yun. We will see you again. Before we usually we have the documentation session, photo session, Professor.
Okay.
So from the one in the Zoom, you can you open your video and we will have photo session. Mbak Safira bisa cover.
Baik, Pak. For all of the participants, please turn on your camera. We will taking a picture together. Okay, for the first page, smile. Okay, second page, third page, fourth. Okay. Yeah, thank you.
Makasih Mbak Safira. Thank you very much, Professor Yun. So
Thank you very
I will
much.
contact you again.
Okay.
Thank you.
Have a great time.
Bye. Thank you very much.
Bye.
Bye. Oke, mungkin sesi untuk hari ini kita cukup. Salah satu ini merupakan program dari UI Resolve, di mana kita mengundang ada total sekarang berarti 3 profesor, yang satu dari yang satu dari MTU, yang satu dari Postek. Memang program ini disediakan untuk mengundang profesor yang QS-nya tinggi ya. UM itu sangat bagus di atas 100, kita kan masih 250-an gitu. Itu seperti itu. NTU apalagi Postek itu yang saya bilang tadi salah satu top 5-nya dari Korea Selatan. Saya sih berpikiran bahwa ini program ini disesuaikan dengan kelas saya karena Profesor Yun pun merupakan expertise di hydrogen energy. Jadi jika kalian yang tertarik dengan